Hello everybody and welcome back. My name is Kinetics, and in today's video I'm going to be walking you guys through problem B, Moamen and K Subarrays from the Code Forces Contest 1557. And this is a Div 2 round which I personally competed in. I did put my solutions onto USACO Guide, so if you want to find the actual physical solutions there, it's in a pull request. Hopefully it gets accepted relatively soon, so you guys should be seeing that there anytime now. Without further ado, let's jump straight into the problem. So the problem states Moamen has an array of n distinct integers, and he wants to sort that array in non-decreasing order by doing the following operations in order exactly once. And make sure we understand that he does this in order. So he splits the array into exactly k non-empty subarrays, such that each element belongs to exactly one array. And he reorders these subarrays arbitrarily. And finally, he merges the subarrays in their new order. So what they mean by he reorders the subarrays arbitrarily is you can choose what the ordering is that you want it to be. So if you wanted to sort it such that you put the first array, and then you put the first subarray, then you put the second subarray, then you put the third subarray, you could do that. You could also change it so you did the first one, then the third one, then the second one, whatever really floats your boat. And it's our challenge to figure out if it's possible to split the array into exactly k non-empty subarrays such that the element belongs to exactly one subarray. And hopefully you all know what a subarray is. This one means contiguous subarrays. So you want to tell Moamen if there's a way to sort all the arrays in non-decreasing order using the operations written above. Luckily for this problem, you don't actually have to specify the order, but I'm pretty sure you could just as easily do it. So your goal is to tell Moamen if there is a way to sort the array in non-decreasing order using the operations written above. So that's going to be a yes or no. And if you take a look right here, let me do a web capture. So capture full page. So if we take a look right here, some things to notice. Number one, you have a 10 to the 3 test cases. And number two, n is 10 to the 5th. So you need to be n log n or less, right? And finally, each of the AIs can be negative. So that's something you got to keep track of. They are less than 10 to the power of 9, but they can be negative. And they're less than or equal to 10 to the power of 9. Again, this should tell us something else. And finally, and I think this is the most important thing, and it's actually why my solution works, it's guaranteed that all of the numbers are distinct. And that's the most important thing. So I'll close this. So it's guaranteed that each number is distinct. Now what this means is, well, let's discuss what we would want to do here. So we're going to take the case, we're going to take the case 6, 3, 4, 2, 1. So 6, 3, 4, 2, 1. And what we want to do here, let's just undo those. So what I want to do is split this into exactly 4 groups such that I can reorder these groups and it'll be sorted. So we take 6, 3, 4, 2, 1, and we reorder this into 1, 2, 3, 4, 6. And just for reference, here are the buckets, I guess you could say, or the subarrays. So that's what it would look like. Now my question to you is, let's just observe this subarray. What do you notice about the order of its elements? Well, the order of its elements stays the same. So inside the subarray, the order of the elements stays the same. So if we know this sorted array beforehand, we can just check, is this subarray going to be the same before and after, right? Is the order of the elements going to be the same before and after? If so, you can put them in the same subarray. So that leaves us to an observation which we'll cover shortly. But first, before we do that, I just want to ask you something. If you can do it in, suppose, M moves, can you do it in K? The answer is yes, you can, because you can always break up your subarrays into even smaller subarrays. So if I can do it into K moves, in M moves, can I do it in K? And what I meant is M is less than or equal to K. I should have probably specified that. Yes, you can. Right, so if we find the minimum number of moves, then as long as that's less than or equal to K, we're done. And minimum number of moves, I actually don't mean moves, I mean subarrays. Right, so what we want to do is break this up into as few subarrays as possible. And what we do to do that is we employ a greedy algorithm. So our algorithm is as follows. Step 1 is to sort the array. So if we're given 6, 3, 4, 2, 1, we sort it into 1, 2, 3, 4, 6. For each element, we keep track of the element before it. I think, yeah, before it. So before it is 1, before it is nothing, before. It might be after. You can also definitely do it as after. Actually, I think the way I implemented it is as after. Yeah, I did after. So I did after. So it's going to be like this. And all we're doing is we're just storing the value after it. So right here, 1 has 2, so we're going to keep this in a map. And this is going to be our map. 1 corresponds to the value of 2. 2 corresponds to the value of 3. 3 corresponds to the value of 4. 4 corresponds to the value of 6. And let me just undo that to get a bit more space. 3 corresponds to the value of 4. 4 corresponds to the value of 6. And 6 corresponds to the value of not negative 1, because remember you can have negative numbers, so we're going to make it infinity. So 6 corresponds to the value of infinity. Now all we got to do is check from this index all the way do we have to create a new subarray there? So what I mean by that is if you take a look at 6 and 3, you can never put these in the same subarray because in their sorted order 3 is not preceded by 6. In other words, you're never going to find 6 and then immediately find 3 in this list. And the reason we know that is because if you take a look at what's after 6, that's infinity. That's not equal to 3. Since it's not 3, you know you have to at least have a subarray like this. Now if we take a look at 4, well, 3 after that is 4. Yes, we can have 4. So what we're going to do is keep them in the same subarray. Now if you take a look at 2, well, 2 is going to be, well actually 4, the thing after 4 is 6. 6 is not equal to 2. We have to create another subarray. And I think you guys get where this is going. Just keep track of the number of subarrays. So here, one more subarray. So plus 1 is equal to 2. Here, one more subarray. So plus 1 is equal to 3. And then for 1, again, if you take a look, what follows 2? 3. 3 not equal to 1, create a new subarray. Right here, plus 1 is equal to 4. So at minimum, we need 4 subarrays. And that's just following everything that's right here. Using this map of values to the values that are after them, we determine that this is what is the minimum, because we're always greedily trying to put as much into the same subarray. Why does the greedy algorithm work? Suppose we have some subarray here, so A, B, C, D, and then one more subarray here, E, F, G, And suppose in the sorted order you got D, and D, and then E, and then Well, you want to merge these. Because D and E are contiguous, it's guaranteed that you can merge these two. You can always combine these two and use one less subset. Because, well, one, we know this is how it's going to appear, so we know you've got A, B, C, and then D, and we know you got E, F, G, so we know you got A, B, C, D, E, F, G. So you always want to merge as greedily as possible. So as long as you keep pushing back, you're good to go. So that's basically the explanation of the greedy algorithm we're going to use here. A bit of a time complexity analysis. We're using a sorting so that it automatically bumps it up to n log of n. And if we take a look at the rest, well, you're using a map. If you really wanted to, you could use a hash map and reduce it down to O of n. Don't do that because at worst that actually becomes O of n squared. So instead, use a sorted map that's again n log n operations. And the reason being, we've got this, we're iterating over each element once, so that's n. If you use a sorted, if you use a hash map, you have the possibility of running into an n squared algorithm. If you don't use a hash map and you use a ordered map, for some people it's called a tree map. If you're in Java, in Python, it's just a map, it's a dictionary. It's going to be n log n, so you've got two n log n's. That's just going to be O, and this big O of n log n. So that's the time complexity, and as we observed before, that should run in time, which it does. So for the code, here's the C++ code that I wrote in competition. So I kept track, and let's break this down right here. I first read in the input n and k, and then I read in the arrays. So I read in just one array, and I set, this is SAR, and I don't know why I named it SAR, I can't remember right now, but I did, it's a duplicate array, it's gonna be, oh yeah, it's sorted, that's why it's called SAR, it's gonna be sorted array. So for now, we just read the same array basically twice, and then we sort the array, and this is a map called next. And if you take a look, that's basically what this is doing. So I said for I to n minus 1, we're going to initialize next, and then for the n minus 1th value, we're setting it to mod, and the reason for this mod is for me, it's 1e9 plus 7, so that is equivalent to infinity for our purposes. So just set the last one to basically be infinity. And then we have int answer equals 1, and again, that's what I talked about right here. And we're iterating for I from 1 to n. If next of r of I minus 1 is not equal to r of I, basically what that's saying is, if in this, so if we take a look at this index, for example, 3, so we've got 6 and 3. So we've got r of I minus 1, that's 6. If we take a look up in our table, that's next of r of I minus 1, we get infinity. If that's not equal to r of I, then we have to add 1 to our answer. And then if answer is less than or equal to k, we can sout yes, otherwise sout no. For Java, this is the solution that I did out of contest. This is pretty standard input-output, and then we're reading in our integers. Again, same thing as the C++. We have these arrays where we're reading stuff in. I'm using arrays.sort. Here it's a tree map. You could use a hash map if you want. Again, I don't like using it. I used to use it, now I don't use it. It's really up to personal preference. And so we're putting in SAR of I, and that's essentially what we did here, where we were just initializing this. We're just putting SAR of I plus 1, just a map, the way we talked about. And then again, we're putting this int 1e9. Yeah, this is actually a bit risky. I don't know why this passed. You should definitely put plus 7. It passed for our purposes, but if it didn't pass, that's probably why. So I would actually just do that right now, plus 7, because that way you know it's infinity. And then the same thing here, if we're saying next.get of r of I minus 1 is not equal to r of I, right? And this is answer plus plus, and this is get because it's a map. And that's it. After that, same thing. In Python, this is what we have. This is standard test case input. We're using reading in our two integers by mapping them to the int function, and we're doing the same thing, except now we're taking a list and we're doing array.copy because we don't need to do a deep copy. It's only one value, and we're sorting it. We're creating a dictionary called next. You don't actually want to create a dictionary called next. I think I changed it to after. That way, because next actually has a meaning in Python. So if you take a look at the USACO guide, use that solution, not this one. For in range and -1, again, same thing. We're just updating the values. It's exactly the same as the C++ code, right? So after that, we're setting it to int of 1e9 again. Do +7, and then answer is equal to 1 for I in range 1 to n. If the next is not equal to the array, answer plus equals 1. And then if answer is less than or equal to k, print yes, else print no. You could probably simplify this to, I did this again, same thing in USACO guide, that's how it is. Print yes if ans is less than or equal to k, else no. That's a cool use of ternary operators. And that's pretty much it. That's all there is for this problem, and let's just go ahead and submit all of these and pray that nothing happens or breaks. So we're submitting it, and it's in queue because it's kind of busy. Let's do Java 11. We're gonna submit this, and again, pray that this doesn't fail. Yep, so that one's accepted. And that one's also accepted, and this one is a Python. I used Python 3.8.10 because it should have the same functionality. And again, accepted. I want you to notice something here. Look at the speed of Python and look at the speed of Java. For some reason, Python is faster than Java, and I don't know why. It uses less memory. This was really mind-blowing to me because I've always felt like Java is faster. Maybe I should be using Java 8, I don't know. But yeah, I feel like Java is becoming a bit outdated. Anyways, enough rambling. Here's the C++ code, since I mainly code in C++. So yeah, and one last thing I want you to notice, this is 16 lines of code, this is 44 lines of code. They do essentially the same thing. So yeah. Anyways, that's all for this video. I really hope you guys enjoyed. If you did, please don't forget to like and subscribe, and I'll catch you all in another video. Goodbye.